Okay, in the last video, we were able to derive an expression that would give us the amount of work it would take to move a test charge here, a test positive charge, from point A to point B when there is a single isolated unit of positive charge here. And we found out, somewhat to our surprise, that the amount of work that's required to move the test charge depends only upon the initial separation and the final separation. It is totally independent of the path in between our initial starting point and our end point. So that if we move our test charge along this path, or whether we moved it along this path here, where it might be 3 or 4 times longer, the amount of work that is performed is exactly the same. And we said that this is a hallmark of conservative systems, that when the amount of work being performed is independent of the path length, it depends only upon the initial starting point and the end point here. And we had a way that we summarized this, because this is what the work integral is, and what we said was that for conservative systems, F back L over a closed loop is 0, so that if we start here at point A, we went all the way around to point B, then after that we took another very long and laborious convoluted path back to point A. The total amount of work performed in moving that test unit charge all the way around that long, complicated path was 0. And again, that is another hallmark then of conservative systems. Electrostatic forces behave like that, gravitational forces behave like that, but not all forces do. For example, if there's friction in the system, then it's not going to be conservative, because for a frictional force, F dot dl is always positive. So the integrand can never be negative then, or can never be 0. But now for conservative systems, where we do have this curious property, let's ask this question then. Since the amount of work that's performed depends only upon the initial point and the end point, and whether a short path or a long path has nothing to do with it, then for a conservative system, is it possible to express the amount of work going from A to B as simply the change in some scalar quantity whose value depends only upon the position of the endpoints, or we should say only upon the position of the beginning point and the end point. So in other words, if we're dealing with a conservative system, and we're standing here at point A, and we end up here at point B, is there some scalar quantity that exists in these conservative systems that might have a certain magnitude at point A, has a different magnitude at point B, and then when we move the particle from point A to point B, the difference in quantity of that, the difference in magnitude of that scalar quantity, would that be equal then to the amount of work that's performed? Does such a quantity exist? It depends only upon the position points here, and the difference in magnitude of that is what determines how much work is performed. Does such a thing really exist? And to answer that question, we have to go back and think about the gradient vector. Now, here, we just have some function f of x, and we're at a point x, and f of x has a value here, and then let's say that we have a small differential dx, and now we're going to take f of x dx, and say that gives us this point up here. So we went from this point of f of x to this point f of x dx. Is a straight line that connects those 2 points, and we want to ask, well, how much does f change over this distance dl? What is what is df over that distance? And the answer is df equals the gradient of f dot dl. And again, we covered this quite thoroughly in our introduction to the del operator. Now, we're performing trying to say compute the work done in an electrostatic field or gravitational field. Now we're dealing with a line integral like this. Its general expression, f dot dl, going from A to B. Now suppose that, when the vector f is the force vector, suppose that this force vector was the gradient of some scalar quantity. Suppose that f was the gradient of some scalar quantity, we'll call it v. Then, the amount of work that's being performed, going from A to B, that would be equal to, if I go from A to B, f is this, so we would have del v dot dl. But del v dot dl, that's dv. That's what the gradient vector is all about. So this equals and that, of course, would just be equal to that scalar evaluated at point B minus the magnitude of that scalar evaluated at point A. Now, if you look in the physics and engineering books, you'll see that the force is usually not taken as the gradient of some scalar, but it's actually the negative gradient of that scalar. So this would have a minus sign here, and this would be going from B to A, and this would be VB or VA minus VB. But now, and that would be the amount of work performed. Now, if we're just going from point A back to point A again, starting at point A, going back to point A, dV, well, clearly dV is going to be 0. That would be like here, then we're going to here, then we're going back to here again, and we're asking ourselves, what is dF? Of course, it's 0. So this means then that which of course is the hallmark of a conservative force system. So the point here is this, is that if the force that's doing the work is in fact equal to the gradient of some scalar quantity, or more technically the negative gradient of some scalar quantity, that will be a conservative acting force. That's point number one. And we can see that, yes indeed, it depends only on the endpoints, but there's a more important point here, and that's this, is that the amount of work being performed, we said, all right, suppose that our force vector is the gradient of some scalar quantity. So VA, that then is the magnitude of our scalar at point A minus the magnitude of our scalar quantity at point B. And that's what we were asking ourselves, though, in this question here. We asked ourselves, well, we're in a conservative system. Is there some scalar quantity that exists that has a certain value here and a different value here, so the difference in the value of that scalar quantity is what determines how much work is performed? And the answer to that question is yes, we see it right here. When the force is equal to the gradient or the negative gradient of that scalar quantity. And there's a name for that scalar quantity. It's called the potential. So we see that when F is this, then F dot dl let's express it more generally, is 0. Now, let's ask ourselves this question. If we start with this, can we work backwards and determine this? And that's what we're going to do in the next video. So stay tuned. We're almost finished with this topic on conservative systems, but there's one more aspect here that we have to explore, and we'll do that in the next video. So come back, join us for that, and we'll try to wrap up this topic.